Have you ever wondered how organic compounds are classified? It is indeed a question that has intrigued many minds for years. To initiate our exploration, it is crucial first to get the basics right. Organic compounds, at their core, are carbon-based molecules. This might sound rather simplistic, yet it reveals an astounding fact about life as we know it. These molecules, humble as they seem, are the fundamental building blocks of life itself. They omnipresently dwell in every nook and corner of our existence, the food that provides us with the necessary nutrients for survival, the air that we inhale every second. They all are abundant with organic compounds. The complexity of these compounds can range from a simple methane with just carbon atom and 4 hydrogen atoms, to more intricate structures like ethane, possessing 2 carbon atoms and 6 hydrogen. The grandeur of the organic world doesn't stop there. The sheer volume of organic compounds that exist is mind-boggling. A conservative estimate puts that number in the millions. Yes, you read it right, of organic compounds are out there, each different in its structure and properties. Such a vast array of compounds obviously poses a significant challenge in understanding and studying them. Therefore, it becomes profoundly essential to bring some semblance of order to this almost chaotic world of organic compounds. The solution lies in classification. By classifying organic compounds based on their functional groups, the specific group of atoms within the molecule responsible for a compound's characteristic chemical reactions, we can begin to make sense of this diversity. This classification, more than just categorize, it enriches our understanding of these compounds. It helps us to comprehend their properties, their reactions, and their potential uses. The benefits of this classification extend into various fields, from medicine to material science, underpinning the importance of understanding organic compounds. Understanding the classification of organic compounds forms the basis of organic chemistry. So, let's dive deeper into this fascinating world in our next segment. Stay tuned for an enthralling journey into the heart of organic chemistry. Organic compounds classify into different types based on their functional groups. Now, you might be wondering, what's a functional group? Well, imagine you're at a party. Everyone's dressed up, but the way you can tell them apart is by their accessories: hats, glasses, scarves. In the world of organic compounds, functional groups are those accessories. They're specific groups of atoms within molecules that determine how those molecules will behave chemically. Let's delve a little deeper. Think of alcohols. Not just the kind you find in your favorite drinks, but in a chemical sense. Alcohols are organic compounds that have a hydroxyl or OH group attached to them. This OH group is what makes them alcohols and gives them their distinct chemical behavior. Now let's switch gears and talk about aldehydes. Aldehydes are another type of organic compound, and they have a carbonyl group. That's a carbon atom double bonded to an oxygen atom at the end of the chain. This carbonyl group is what differentiates aldehydes from other organic compounds. Next up, we have ketones. Ketones are similar to aldehydes in that they also contain a carbonyl group. However, the carbonyl group in a ketone is located in the middle of the carbon chain, not at the end like in aldehydes. Last but not least, we have carboxylic acids. These guys contain a carbonyl group and a hydroxyl group, making them quite the combo. Because of these groups, carboxylic acids have specific properties and behaviors. So, you see, functional groups are like the ID cards of organic compounds. They determine the chemical behavior of these compounds and help us understand how they'll react in different situations. Now that we know how organic compounds are classified, let's get to naming them. Ever thought about how organic compounds get their names? Well, the answer is hidden in the sophisticated system of nomenclature established by the International Union of Pure and Applied Chemistry, commonly known as IUPAC. Imagine a world where everyone had the same name. Confusing, right? The same goes for organic compounds. With millions of them in existence, scientists needed a systematic way to name them, thus the birth of IUPAC nomenclature. The IUPAC system is a set of logical rules devised and used by organic chemists to circumvent problems caused by arbitrary nomenclature. Knowing these rules and given a structural formula, one should be able to write a unique name for every distinct compound. The first rule is to identify the longest chain of carbon atoms, which is called the parent chain. The parent chain's name is determined by the number of carbon atoms it contains. For instance, a chain with 3 carbons is called propane. Next, we look at the branches or substituents coming off the parent chain. These are named based on the number of carbons they contain, with a prefix indicating their position on the chain. For example, a branch with one carbon atom is called a methyl group. Then we put it all together. The name of the compound is written as one word, and we use numbers to indicate the position of the substituents. Let's take an example. A compound with a 3-carbon chain and a methyl group on the second carbon would be named as 2-methylpropane. There are, of course, many other rules and exceptions in the IUPAC nomenclature system, including those for naming cyclic compounds, compounds with double or triple bonds, and compounds with functional groups. However, the basic principles remain the same. Naming organic compounds might seem complicated at first, but with practice, it becomes a piece of cake. Just remember, every organic compound has a unique name, just like you and me, and just like learning new names, the more you practice, the easier it gets. Now, let's delve into how electrons behave in a covalent bond. Covalent bonds are the heart of organic chemistry. They are the ties that bind atoms together to form molecules. But these bonds are not always equal. Sometimes electrons get pushed around a bit, and that's what we call electronic displacements. Let's start with the inductive effect. Imagine a tug of war, with electrons being the rope. In this tug of war, one atom pulls electrons towards itself more than the other, creating a slight charge imbalance. This is the inductive effect, a permanent state of affairs in a molecule, where the electrons are not shared equally. Think of chlorine in a hydrochloric acid molecule. It's more electronegative, so it pulls the shared electrons towards itself, creating a partial negative charge on it and a partial positive charge on the hydrogen atom. Now let's move to the electromeric effect. This effect is a bit like a surprise party. It happens suddenly and changes the scene completely. It occurs when a reactive species approaches a double or triple bond. The p electrons of the bond shift entirely towards one of the bonded atoms, creating a positive charge on the other atom. Once the reaction is over, the electrons move back, and everything goes back to normal. An example is the addition of a proton to an alkene to form a carbocation. Remember, these effects are all about the movement of electrons, and electrons are the driving force behind chemical reactions. By understanding these effects, we can predict how a molecule will behave when it comes into contact with other molecules. Understanding these effects helps us predict the reactivity of organic compounds. So next time you're looking at a complex molecule, remember the tug of war and the surprise party. They might just help you figure out what's going on. We've covered a lot of ground today, haven't we? We started with the basics of organic compounds, understanding their unique characteristics and importance. Then we delved into the classification of these compounds, exploring the vast array of categories they fall into. We also took a deep dive into the IUPAC nomenclature, a universally recognized system for naming organic compounds. Finally, we examined electronic displacements in a covalent bond, specifically the inductive and electromeric effects. There's a lot to take in, but with practice you'll master it. Try naming some organic compounds on your own or sketching out the electronic displacements in different covalent bonds. This hands-on practice will reinforce your understanding and make these concepts second nature. Thank you for watching this video. Don't forget to comment with your thoughts or questions. Like this video, share it, and subscribe to our channel, Facts Academy 0122 for more enlightening content.